Hey everyone, we're back. It's time to talk some more about these infinite series that we introduced last time. Weren't they great? We introduced the idea of adding up the terms in a sequence, an infinite sequence, to create what we call an infinite series. And then our job is to determine whether that series converges or diverges. So here's an example to get us going. And one thing to ask yourself when you're looking at a series is, what kind of structure does this geometric series have? We've already seen two types. We saw the telescoping series where things expanded out and then there was a lot of cancellation, and we could find the partial sums that way. And then we saw these geometric series where we could actually, in general, calculate the partial sums and come up with this theorem that tells us how to treat them once we know what R and C are. And because this theorem gives us such a powerful tool to work with geometric series, a good thing to ask yourself is, am I looking at a geometric series? And I kind of talked about this a bit last time. My idea here is to rewrite the series. I'm going to call it S, hoping it converges. S will be a finite number, otherwise S will go to infinity. Well, S will be, it won't be a finite number. But the first thing to do if you want to decide if this is geometric is to factor out that leading term, factor out that leading constant. I think this is the easiest way to see. Because if this is geometric, that constant will become our C. But more importantly, what we're left with, if this is a geometric series, what we're left with here must be of the form 1 plus r squared plus r cubed, and so on. And so in this case, I factored out the 3, and I'm left with 1 minus 2/3 plus 4/9 minus 8/27. And the question is, what number would I multiply 2/3 by to get 4/9? Well, the answer, I think, is clear, is 2/3, because that produces 4 on top and 9 on the bottom. What number would I multiply 4/9 by to get 8/27? And the answer there is 2/3. We double the numerator and triple the denominator. And so this appears to be geometric, because this is 1 minus r plus r squared minus r cubed, where r is 2/3. But hang on, that doesn't match that. But how about if r, maybe you can't see that color, what about if r was itself negative? Because we can say, if I start with negative 2/3, or let's even start with 1, what number would I multiply 1 by to get negative 2/3? The answer is negative 2/3. What would I multiply negative 2/3 by to get positive 4/3? Right, I'm thinking about the values that are appearing in the sequence. And the answer is negative 2/3, negative 2/3. In other words, I can write this sequence as 3 times 1 plus, I can write it as 1 plus r squared plus r cubed, where r is negative 2/3. So this series is, in fact, geometric. So you can check it. Minus 2/3 all cubed is 8/27 with a negative sign. This is 4/9 with a positive sign. And so we've got C, that's the number out the front, it's 3, and r, in this case, is negative 2/3. And so putting all of this together, we have a series which is geometric, and where this is the C and R value, and just looking at the theorem that we have down at the bottom of the page here, the absolute value of R is the absolute value of minus 2/3, which is 2/3, which is less than 1, and since it's less than 1, the series converges. And not only does it converge, but this tells us a formula for the convergent value. So in here, this thing has to add up to 3 over 1 minus 2/3, right, which is 3 over, what does that make it? 5/3. 3 over 5/3, and that's going to be 5, well, no, it's not. It's going to be 3 over 1, if you like, multiplied by 3/5. So that adds up to 9/5. So we're able to say that this is an infinite series that converges. There's the infinite series up there. This is an infinite series that converges, and it converges to 9/5, just through a little bit of algebra. And it relies on this test of the R value itself, and the R value we got by looking at the series and checking things out. So let's have another go at one of these. All right, so let's look at another couple of examples. This one, looking at it, using the same approach as last time. Maybe this is an infinite series, so I would go ahead and pull out that first term and then go searching for R, right? So this is 1 plus 3/4, because I pulled out the 4, and then 1/4, and then I'm going to have an 1/8, and the next one's going to be 7, what's 4 sevens? 4 sevens are 28, so 1/28 plus dot, dot, dot. Right? I ran out of room there. Plus dot, dot, dot. And so we look at that and we say, well, maybe this is a geometric series with C is equal to, it's the number out the front, so C is 4. And then the first term that's not just 1, that could be our R. But then remember that R, if it's 3/4, I need the next term to be R squared and the term after that to be R cubed, right? And if R was 3/4, then R squared would be, well, it would be 9/16. And R cubed would be 3 cubed is 27, 4 cubed is maybe 32. No, that's not right, 64. And that's not these next values. So this series is not geometric. And so I really don't know right now what to do with it. But it's really important to remember that we've got a hammer down here. This geometric series is a hammer, but not every series is a nail. This is not a geometric series, and so our thinking doesn't help. All right, the thinking about the geometric series doesn't help if it's not geometric. So let's look at another example. Here's a series again that might look geometric, and so we can pull out that first term, and that first term this time is -2, which leaves us a 1, because that's what we want. If we're looking for a geometric series, that has to be a 1 in the leading term. But then what I'm left with is a 3. Oops, that was weird. I'm left with a 3. The next one, I pulled out the -2, so that's a 9. The next one, I pulled out -2, so that's a 27. And so you can very easily see, I think there, that this one is geometric. This is 3 to the 1 and 3 squared and 3 cubed, and that's exactly the feature we expect to get with a geometric series. And comparing it, that tells us that C is -2. That's the number we pulled out the front. And then R is 3. Does it converge? Well, hopefully again you can see that it doesn't. The important thing here is that the absolute value of R is bigger than 1. And as soon as we know that the absolute value of R is bigger than 1, or in fact bigger than or equal to 1, the series diverges. And in fact it diverges so that the partial sums head off to -infinity. Right, because I start adding up the partial sums here. Remember the partial sums from last time. These are an important tool when we're thinking about series. So the partial sums are what we get when we add the first term, which is -2. Or the first 2 terms, when we add them, we get -8. Or the first 3 terms, what do we get? -26. Or then we add -54 to that, which I think is -80. So as we keep going down, the nth partial sum is just going to get bigger and bigger and bigger. And so these are going off to -infinity, and the geometric series diverges. All right, so let's look at another example. In this case, we've got an infinite series which is just the sum of the number 1 from 1 to infinity. So the way that we look at these things is also to look at always to look at the nth partial sum. And remember here we're just adding 1 many times, so the first partial sum is 1 and the second partial sum is the first 2 terms, which is 1 and 1, and the third partial sum we're adding the first 3 terms, which is 1 and 1 and 1. So you can see what these sums are giving us, and so from that we can conclude that the nth partial sum must be, well, it must be n, right? We've added the number 1 together n times. And so we've got the nth partial sum. To determine whether the full series converges or diverges, we take the limit. And the limit of the nth partial sum in this case is just the limit as n tends to infinity of n, right? Because that is our nth partial sum. And if n's going to infinity, well then n's going to infinity. And that means that our series diverges. Which may be a bit silly. In this case it's a pretty simple series, but you can imagine if you added any series where you're just adding a constant number like this. So if I added 1/5 together over and over and over, that's also going to diverge, right? That series is also going to diverge because the nth partial sum in this case would be n over 5, because we've got a fifth plus a fifth plus a fifth. We're doing it n times, so we get n fifths. And so it would diverge as well. And so there's a quick way to see whether a series will diverge, and it's called the divergence test. And here it is from the book. In fact, they call it the nth term divergence test. And it basically says, if the limit of the terms aren't 0, then the series diverges. And in this case, think about the limit of the terms in this case. If the terms here were adding up 1 each time, right? So this is our nth term. I've lost my pen. But this is the nth term. It was just a 1. And so the limits of the nth term in this case, as n goes to infinity, of 1, well, that limit is obviously 1, and it's not 0, and so the divergence test immediately tells you that the series diverges. Because think about what this is doing. Eventually, your numbers are going to get closer and closer to the limit. This is the limit of the term, so we're looking at the limit of the terms in the sequence. And if those limits of the terms in the sequence, right, the sequence is just a list of numbers. And so if I say the limit of the terms in the sequence is approaching some value, let's say they're approaching 5, then that means as I write down the sequence, those numbers are getting closer and closer to 5. And so when I write down the series, what I'm doing is adding up all those terms. So eventually I get to the point where my numbers are almost essentially 5, right? Close to 5. So from then onwards, I'm adding something that's really close to 5 to something that's really close to 5 to something that's really close to 5 to something that really... So just like our previous example, that must diverge because I'm adding a number that's essentially 5 forever. And so that's the key idea in the divergence test. If the numbers don't go to 0, if the limit of the terms in the sequence don't go to 0, then the series that you get by adding those terms together must diverge. And so this divergence test avoids us having to look at the nth partial sum, but the nth partial sum is the thing that's really breaking it underneath because you're eventually adding up things that don't go to 0, and so that's going to be really big in the long run. Let's have a look at another example. So we want to determine if this series converges or if it diverges. And again, we can, just for practice, just to get an idea of what's happening here, we can start writing out terms in the series, right? So when n is 1, you get 1 over, well, that's 3 times 1 plus 1, that's 4. And the next term is 2 over, well, 2 times 3 is 6 plus 1 is 7. And then the next one is 2 over 3 times 3, which is 9 plus 1, which is 10. So each time we're just adding 3 to the denominator, right? 4, 5, 6, 7, 8, 9, 10. So we've got 2 over 13, and then 2 over 16, and then that continues forever. There's our infinite series. The question is, does that diverge? And one way to check quickly is, or to check whether it converges or diverges, one quick thing to ask is, does it diverge? Because the divergence test is really easy to apply. And so if we can say the divergence test tells us immediately that this thing diverges, then we're done. There's nothing else to do. We don't have to worry about whether it's a telescoping series or a geometric series or do any of the things we've talked about so far. We just need to think about what happens to the terms as n goes to infinity. So what's the limit as n goes to infinity of n over 3n plus 1? Because that is the general term, n over 3n plus 1. So this is a Calc 1 problem. Right? You can use L'Hopital's rule by converting it to a continuous function and writing it as x over 3x plus 1, but you don't need to do that. If I divide top and bottom by by n, then you get that. 1 over n goes to 0, right? I multiplied this top and bottom by 1 over n. And when we do that and simplify the algebra, what we're left with is the limit of 1 over 3 plus 1 over n. 1 over n goes to 0. And so this whole thing goes to 1/3. And 1/3 is not equal to 0. And if the limit of that is not equal to 0, the series diverges by the divergence test. That's it. And that's all we need to do. We do need to note that it diverges and explain why it doesn't diverge. Why it diverges. It diverges. The limit of this series doesn't exist. When I add it up, I will not get a finite number. And that's because the limit of the terms goes to 1/3. And so the idea here is these numbers are eventually getting really close to 1/3. And so when I add them all up, I'm just adding a third and a third and a third and a third forever. And so that must go off to infinity. So this series will diverge to infinity, and the divergence test is what tells us that that is what's going to happen, which is cool, right? Nice and simple to use. All right, here's another example of an infinite series. This one is the sum of 1 over n. So 1 over 1 plus 1 over 2 plus 1 over 3, you get the idea. And this series has its own cool name. It's called the harmonic series. So the question is, does it converge or does it diverge? Well, we can always check, and we always should check, the divergence test, which means calculating the limit of the nth term as n goes to infinity. And the nth term is precisely what we see there. It's 1 over n. And so Again, easy limit to calculate. That's 0. So what can we conclude from our theorem? Our theorem says if the limit is not 0, if the limit of the nth term is not 0, then the series diverges. Well, the limit is 0. So the test tells us nothing. Right? It tells us nothing. It's no help at all. It's really important to realize this because the test is an if-then statement. It says if something happens, and in this case, the if is if that limit is not 0, then something happens. And that something is the series we're thinking about diverges. But we don't have a limit here that's not 0. The limit is 0, so it could converge. Or it could still diverge. The test tells us nothing, so we've actually learnt nothing. Right? We've learnt nothing at all. The series could still converge, or it could diverge. This divergence test doesn't apply, so it doesn't tell us that it diverges, but that doesn't mean that it converges. You get what I'm saying? This test tells us no information. So it's not telling us that it converges, it's telling us that the test fails to actually tell us anything at all. All right, and this is an important idea because it's easy to misapply this test. This test says if the limit, as n tends to infinity, of the nth term in the series, if that doesn't go to 0, then the series diverges. Otherwise, it gives us no information and we're left completely in the dark. So that's where we're going to leave it. We're going to leave it completely in the dark. We're going to come back to our friend, the harmonic series, soon enough. But let's finish today by looking at just the linearity theorem that relates to these limits. Okay, so finally the linearity theorem, it just tells us some things we can do with series. Series are just a bunch of things added together, right? So if you look at this first one, all I'm saying is if I'm adding things together, this is, the sum of, I'm going to just write this out. If I think of what this series is going to give us, the sum of a sub n plus b sub n, that's going to be, a1 plus b1 plus a2 plus b2, and so on. And we can just rearrange those if they converge. If we can rearrange these things and write them that way, right? And then you can imagine rewriting this first one as the sum of the a-n's and this second one as the sum of the b-n's. So you can see how that kind of works. And it only, in fact, what's weird about series, and we'll see this a bit more, it only works if this converges. If it doesn't converge, you've got to be really careful, and we'll talk about that later. But right now, if I have two series that converge, the series that I get by adding up the sequence of numbers a sub n, and the series I get from adding up the sequence b sub n, then I can add those numbers and the series will converge. I can take their difference, I can multiply by a constant, all of the series will converge, and they'll converge to the obvious thing that you would expect. In other words, this idea is linear. We can split it into the sum of the a's and the b's separately. So I'll do an example down here. I've given a series here that can be written as I've given a single series down here, but think about that. I can rewrite that just doing a little bit of algebra as 3/4 to the power of n over 5 over 4 plus 5 over 4 to the power of n, right? So there's really two series going on here. If these things converge, so we can use this to split them into two different series. If the two individual series, this series and this series, if they actually converge themselves, then what they converge to will equal that original series that we had. And so we can look at each of these, and each of these is actually a geometric series, because I could start writing it out. That's often the easiest way to see it. And I'm using n here as my summation variable. Sometimes I use I, sometimes I use n. It doesn't matter. So if we write those series out, you can see the one on the right here. I factor out the 5 over 4, and I'm getting a geometric series here. And it's geometric with the c value being 5 over 4 and r being 1/4. And doing a similar thing to the other one, we see that it's also geometric. And in this case, c and r are both 3/4. So taking all of that information, let's go on the next page just so we've got some space. We can complete both of these sums because remember the geometric series, if it converges to c over 1 minus r. So in this case, we get 3/4 over 1 minus 3/4. If it converges, well it does, because the value of r in this case is 3/4. Right, I'm kind of off to the side doing this calculation now, and then I'm going to go off to the side and do the other calculation, and it converges since r in this case is 1/4, and so this converges to c, which is 5/4 over 1 minus r, which is 1/4, and if we work these things out, we get 5/3 for this one, and in this case we end up with 3/4 divided by 1 minus 3/4 is 1/4, and so that's going to be 3. And so that lets us put the whole thing together. So we've got two constituent series here, right? We've calculated this series and we got 3. We calculated this series and we got 5/3. And so we can use the theorem to say, well, this final result is just the sum of those, which is going to be, what, 9 plus 9/3 plus 5/3 is, I think, 14/3. And so there is the sum of that original series we had, and we got it by breaking it up into two pieces and working out that those two pieces individually converged, and then so the total series converges to the sum, as you'd expect, right? All right, so let's leave it there for today. I hope this has made sense. These ideas are new, they're different, you're going to have to play with them, you're going to have to do some web work, do some initial practice problems. Come see me in office hours and I'll help. Have a great day.